So continuing with our similarity unit, we're going to look at what's called the triangle proportionality theorem. And what this theorem says is if a line parallel to one side of a triangle intersects the other two sides, then it divides the two sides proportionally. So in this picture, all right, notice we've got the arrows which signify that these lines are indeed parallel. So if we just kind of imagine that middle line extended, we've got our fractions right here. So we can say the top over the bottom will equal the top over the bottom. And very simply, that will be your proportion. And then you cross multiply, so we'll have 4x equals 12, x would equal 3. All right, so obviously 2 over 4 is 1/2 and 3 over 6 is 1/2, so that makes sense. So this is also called the side splitter theorem. You'll see some geometry books, it's called that, and in others, it's just called the triangle proportionality theorem. All right, so again, look for those parallel lines, imagine that being extended, and you'll have a fraction on the left, fraction on the right, there's your proportion, you're done. Now, this is important because if one of the missing sides is actually one of the parallels, all right, then you're going to need to pull the triangles apart. And what I mean by that, all right, I'm going to redraw this picture. Still keep the 2 and the 4, but I'm going to move the x and the 6 there. So notice if you try to extend, I can't use this triangle proportionality theorem because I don't have a fraction over here on the right. So in a case like this, where you're working with missing parts on the parallel, then imagine you've got your little triangle inside, which has a side of 2 and a bottom of x, and then your larger, which this side is not 4, you have to remember to add those together. So this would be a 6 and a 6. Then you can put and make your proportion. So 2 over 6 equals 6 over 6. Obviously, x will be 2 in this case. All right, so pay attention to that. The side splitter or triangle proportionality theorem only works when you've got a fraction on the left and on the right. So looking at this example, it wants us to find the measure of segment SR, which is right here, this part. So I'm going to give this a variable just to change it up. I'm going to call that y instead of x this time. Okay, so I notice I've got parallels. So if I imagine this extended, and you can turn your paper if you need to, I've got a fraction on the left, 10 over y, and then the fraction on the right, make sure what's across from the 10 is also the top, so 4 over 3. No zigzagging. So 10 over y, and then 4 over 3. Again, make sure top and bottom and across, and that's how your proportion looks. Okay, so cross multiply, we get 4y equals 30. So y is going to equal 7.5. All right. Now, you might not have a triangle, so to speak, I should say, but 3 parallel lines can intersect your 2 transversals, and the same thing happens. The sides will get divided up proportionally. So in this picture, there are tons of proportions we could write. So I could do, let's do a couple of them here. So I could do the side AB over side BC. All right, so that's like the top over the bottom part. So over here, that would equal DE over EF. That's 1. All right, let's do another one. If I did BC over AC. All right, so what I did is the bottom over the 2 parts together, then that's what I need over here. So I need the bottom, which is EF, over the 2 parts together, which would be F. So you're looking for the same patterns. All right. If I did, let's say I did AB over DE. So I did top left over top right. I would need to have one of the parts over here. So if I was given, let's say, CB, all right, then again, I've got top left over top right, and then this one's starting with bottom left, so I need the bottom right. Now, you can call it FE and go in the same directions, or EF. The order of the letters does not matter. All right, so there's lots that we could do here. All right, let's look at this triangle. Well, let's look at the example first. So over here, all right, it wants us to find the measure of segment LM, which is this top part, and the bottom. All right, so I'm going to call the top X, the bottom Y. Oh, and you know what? I'm going to go back real quick. In example 1, we got to be careful. We called it Y, but we're going to need to switch that and make sure that we label it with what they want us to find. So we need to do that down here. So we can assign it a variable, but then we'll make sure we label it properly. All right, so to get the top, all right, I could certainly look at the side splitter thing, but that doesn't work because I've got both variables would be those two parts here. Can't have two variables in my proportion. So what I'm going to look at, what do I have on the left? I'm trying to find the top, and I know the two parts together. So if I do X over 8, again, which is top over the two together, then that's what I'm going to set it equal to over here. So I've got the top, and then I'm going to put the two parts together, which will be 10. Okay, cross multiply. So we'll have 10x equals 32, so x will be 3.2. Now x was LM, so we'll change that out. Now very simply, if this is 3.2, we can just do simple subtraction, right? And to get y. So y would end up equaling 4.8, and that is MN. If you wanted to set up another proportion to get y, we could. So we could now use 3.2 over y equals 4 over 6. All right. You could do y over the 8. So bottom over the whole side would be 6 over the whole side, 6 over 10. It's up to you. All right. Sometimes it's just a matter of subtracting. Sometimes you will need a completely new proportion. Now notice down here, we're back to the triangle. All right. We still have double parallels. Actually, we've got, it would be 3 because that one would be parallel as well. All right. So when you're looking at these problems, not only can we go side to side and create proportions that way, meaning I could do side AD over side EB. So I did the very top left over the very bottom left. So that would equal AF over GC. But because we do have the actual triangle, all right, we might be given these base parts that look like bases. So if I did AD over DF, so I did the left over the bottom of the littlest triangle, then AE, all right, which is this whole side of what I would call the middle triangle, would go over the bottom also of that middle triangle, EG. All right, so we want to look for, make sure that we're combining the whole sides. All right, if I give you, let's see, how about AC over BC? So AC represents the whole right side of the biggest triangle, and BC is the base or bottom of that big triangle. So I did right side over the bottom. Then I could also do AF over DF. AF being the right side of the littlest, DF being the bottom of the littlest. I could also say AG over EG. All three of these would be equal to each other. It's always the right side over the bottom. So over here, all right, I've got an actual triangle. I want to find solve for X and for Y. Well, first thing I notice is that if I can use my side splitter, all right, because right here I've got 6 over 10 equals Y over 14. So I'm going to start with that. 6 over 10 equals Y over 14. So I'm going to have 10Y equals, and 6 times 14 is 84. Divide that out, we get 8.4. So there's Y. But X is one of the parallels. So remember we talked about needing to pull the triangles apart above. So I've got a little triangle that has 6 on the left, 8 on the bottom. And the X is part of what I call kind of the middle triangle. So I need the whole left side, all right? The whole left side is not the 10, it's 10 and 6 together, which would be 16. So by pulling them apart, I can see my proportion needs to be 6 over 16 equals 8 over X. That's one of the proportions that I can write. So we get 6X equals, and 16 times 8 is 128. Divide that by 6. And we're going to end up with 21.3 repeating. Okay. So this is your triangle proportionality. All right. Now, also, we have an angle bisector proportionality. Right? This says, if a ray bisects an angle of a triangle, then it divides the opposite side into segments whose lengths are proportional to the lengths of the other two sides. Sounds complicated, but notice in this picture we've got an angle bisector. So when we draw that in, it splits the side opposite into two other parts. And what they're saying is that, I'm going to call this the left segment. It's my abbreviation for segment. This is the right segment, all right, that we get when we draw that angle bisector in. Well, what the angle that's bisected, there's a left side and there's a right side. So when I go to write my proportion, I've got several ways I can do it. I can put left segment over the left side. And if I create my fraction that way, then I need the right segment over the right side. Oops, lost my M there. All right, so we got to keep that same pattern going. Segment over side, segment over side. If I wanted to do left segment over right segment, then I've got to keep the left over right the same. So this would be left side over right side. All right, so there could be, this varies. You just have to keep the same pattern. So let's look at our example. When I look at the picture, what I notice is I've got an angle bisector, right? So here it's splitting into two smaller segments, 3 and a 5. Now it wants me to find XY, which is right here. All right, I'm going to use the letter A this time since X and Y are my actual vertices. So several ways to do this. All right, if we use this first fraction, I'm going to do left segment over left segment over left side. So I would do 3 over A, and then that would equal right segment over right side, 5 over 10. If I use the bottom one, I would do 3 over 5, and then that would equal A over 10. Notice either way, when we cross multiply, we're going to do the same math. It's going to be 5a equals 30. So a will be 6. But of course, we're going to change that out and call that x, y. Okay, so we got some options, and there are probably other ways that we can write that proportion too. And then just know this. If two triangles are similar, then their altitudes, angle bisectors, and medians are all proportional to corresponding sides also. All right, so in other words, if we've got two similar triangles, this one's supposed to look a little bigger than that one. Remember, your altitude comes down and makes a right angle. All right, so if we know the scale factor here is 4:2, right, or 2:1, then it's going to be the same for the altitudes. That scale factor would be the same for them as well. It would be the same for an angle bisector. It would be the same for a median. All right, angle bisector, we just drew those. Right, so you're going to have your angle split. Whoops. All right, so those would have the same scale factor. And medians, remember, go to the middle of the opposite side. Oops, I guess these should be, actually, no, these would be the same because angles would be the same measure. Sorry about that, but these would not be the same measure. All right, so whether it's altitude, angle bisectors, or medians, whatever the scale factor of the sides is, it's going to be the same for those different parts. All right, so those are your proportionality theorems. You should be ready to do some practice. Tomorrow we will come back and finish the word problem. Okay.